So we crank out the calculations for the gradient descent. We're keeping that operator called expected value. And we're exploiting the fact that the operator expected value is basically a linear operator, and therefore it can pass through any linear functions, okay, without any problems. And sometimes we invoke it, sometimes we take it out, okay? But in the back of our minds, we always believe that the ensembles we have represent a sample of data from the actual data random process that we're dealing with. Okay. So the focus here on us, we view this one as a single layer, meaning that we have an input, we have weights, and in this case we only have a single output. We call it y, and the input, just for simplicity, we call it x, and we have these weights. Keep in mind, if I have a bias, I can also view the bias as a weight with driving input equals 1 or minus 1, right? So this way, I'm not really explicitly showing the bias here, because in this case, I can easily lump the bias with the weights. Okay. So the mathematical, here's the graphical representation on one side, and the mathematical representation is like this. Signals represented by the symbol x sub k, the element, and then the parameter weight. One of these x sub k's equals 1 or minus 1 to denote we're having a bias. And this is the element-wise representation. This is the convert the weight into a vector called w, the input into a vector called x, and we can have a dot product, and that's how we get the scalar output. Okay? And typically we use the error as a metric, and then from the error we obtain a norm, typically the L2 norm, and then we have this particular expression here, which is cost, loss, or performance index, or energy function. All these words are interchangeably used in the variety literature, so if you see it, you should know what this one is. And this quantity is a scalar quantity, and you want to determine basically a procedure that minimizes this cost, which is the loss function, to find the optimal parameters or weights for this particular problem, the process that you have, which is from input vector to an output scalar. And this is a description also of filters, linear filters. This problem is linear. We could see it in a single layer. And we can expand this error squared by this. We can expand this one as such. We exploit the E is a linear operator, can pass through these things. So here we have the linear operator passed, as you can see it, in this term, this term, this term. And then we are looking for a constant weights, optimal weights, not random. So that operator can pass those weights, and we end up with these equations. And we have the expected value of this desired value, which is constant, so it would be the same if it is a constant. And then we have another term here, which is the expected value of x sub k d, which is statistically that's referred to as the cross correlation function between the signal at the output d and the element of the input x sub k. And here's the autocorrelation, which is basically autocorrelation among the inputs. Any questions here? And then we move, if I could succeed in moving this one page down. We view this function now as a function of these parameters and want to decide how we're going to get the right parameters so that this mapping is going to be in an optimal sense, which means going to minimize that cost function I have for the random variable input that I have, corresponding to the label of desire. In this problem description, the label could be any value, could be any analog value, the input could be any analog value, okay? So you walk through this particular cost function, and then typically if we have a function of multi-variables or multi-parameters, like in this case weights, the function of the weights, we take the gradient, which is the first derivative, which is shown here, okay? So the derivative give us the necessary conditions for optimality. So we take the first derivative. If we have a scalar function of a single parameter to determine the min and max, and also other things such as reflection points and what have you, you take the first derivative. The derivative tells you either at a min or a max or a reflection point. It doesn't distinguish between them. But it's necessary for optimality. In this case, we want to minimize, right? So that's the first derivative. Now, if you set this first derivative to 0, then you are at some so-called optimal point. But at this point, you don't know if you're a maximum or minimum or reflection point, first order, right? And think always of a single function from calculus with a single variable. In this case here, we have multivariables, which are the weights. And then this one, obviously, many derivatives, derivative with respect to each one of those w sub k's. So since we have p in this case description, we have obviously p equations like this. We set them all to 0. And if I am careful in collecting these equations, convert them all together, simultaneous equation, into a matrix form. So this is the linear relation. So what I've done here, basically, I took this term here because I set this one to 0. This term, you took it to the other side. You compose a vector, okay, for all the elements of the input. And you have here all the parameter of the weights, which is p. And here you have, basically, you have the inputs. So in this case, we take it to be a square. And then we end up with what's in here, which is the matrix, which is the covariance matrix. Okay, so this matrix, you have a product, it's second order, we call it covariance matrix, between the components, and in this case, you have the cross correlation vector. Okay, and this is the matrix. We have the operator, the expected operator, which means that somehow you need to compute the expected value of these quantities. Okay? And this equation says you are sitting at an optimal point, and you can find the corresponding weights if you solve this equation. The solution of this vector matrix equation gives you the best parameters, which guarantees you're at an optimal point. And we're going back to linear algebra. If somehow I computed this expected value, I end up with a constant matrix here. If somehow I've done that already. Okay? So I have a vector on one side equals to a matrix equal to unknown parameter. Okay? And you need to solve it. And then we look at the properties of this matrix. This matrix necessarily is going to be a symmetric matrix. And we have some nice properties of symmetric matrices, as I referred to last time. This is going to be called the Hessian matrix. Second derivative of the, it's going to be equal to the second derivative of the cost function. Okay? And symmetric matrices, one of the properties they have is that this matrix necessarily does not have any complex eigenvalues. It only has real eigenvalues. Okay? And if this matrix is so-called positive definite, then the solution, the optimal solution we're dealing with here is going to be a local minimum. If this matrix is negative definite, the weight's going to correspond to an optimal point, which is maximum. So we're interested in this matrix, given us eigenvalues that are positive definite. Meaning what? Positive definite matrices, which happen to be symmetric, all you need to look at just the eigenvalues. So really that translates to positive definiteness, translates to eigenvalues all being greater than 0. Okay? If you really want to see that this optimal solution of the weights is sitting at a local minimum. Okay? Because this is just a linear algebra and a matrix, we know more about the properties. In fact, if this matrix happened to be non-singular, which translates to the symmetric matrix, the eigenvalues not being 0, could be positive or negative, we know that this matrix is going to have a solution. Because if this guy is non-singular, just invert it, and you get the optimal weights for the problem. Okay? However, only if this matrix is positive definite is that solution, which is a unique solution, there's no other solution, is going to be a minimum. And because it's a unique solution, that instead of saying local minimum, we say it's actually global minimum. For this problem, when you have a single layer, we know that the optimal weight solution for this problem, okay, is a global minima if the Hessian, which is the second derivative here, matrix, is positive definite, which translates to all its eigenvalues are greater than, explicitly greater than 0. Okay? So I'm throwing all these details to direct you to where you can look into properties of symmetric matrices, and you can have a list of those. And this is one key important things that we are citing here. So for linear single layer network, which is referred to, by the way, this optimal solution is going to be it's called historically the Wiener-Hoff equation, which gives you a linear filter. It's an optimal filter. That's how we get an optimal filter. And it served us so well throughout the years from the 50s and 60s in solving many problems, single layer. And that optimal solution is unique solution, okay? And if we can have this matrix, which is going to be a constant matrix, inverted, we get that optimal solution in one shot. If you're dealing with small problems, that's easy. Just go to MATLAB and invert that matrix if it is a constant matrix. But if you have system with huge parameters, many parameters, okay? Let's say 10,000 parameters. Then MATLAB will have a problem in giving you the inverse, right? That's problem one. Problem two, which we haven't even invoked here, is how can you determine this constant matrix, this expected value? What does that mean? If I have data, which is the x here, and corresponding label, typically label maybe is constant, but we're dealing with random variables, right? Because of the random variables, to compute the expected value, I need to know that probability density if it's continuous random variable, right? I don't know the probability density. So you have to come up with an estimate of probability density in order for you to compute this expected value. So it's not a trivial matter. And people have invested time in going through that route, looking at the data, try to estimate the probability density, then try to expected value. Once they compute it, they plug in and they get the matrix, then they can give it to MATLAB or something else. If it is small problem. If it's large problem, and where MATLAB cannot compute the inverse for you, then obviously, even if you compute the expected value, you get the constant matrix, maybe you have an alternate method. Okay? So that's what the scenario is. But because of the nature of this problem, the single layer problem is no challenge in optimization. It actually has a global solution. The only question is this global optimal solution a minimum and maximum inflection point? And that information is represented or solved by determining this Hessian matrix, which is also referred to the curvature, whether basically the cost function near that point has a concave or convex or reflection saddle kind of property. Any questions on that so far? Excellent. Okay, so the next item saying, okay, we look at using the gradient descent. So what we did here, we computed the gradient, we set the gradient to 0, and we look at the solution for that equation, which assumes that you're already there at the optimal solution. Give me that optimal solution. But how do we get that optimal solution? So this other process saying, I'm not going to compute the inverse. I'm going to compute the gradient here. I'm not going to set it to 0. And here's a cartoon diagram that expresses what it is. You can initialize the parameters. You select some initial value for the parameter. That will result in a gradient value. Let's say you are at this point. Okay? which gives you a gradient here. This is the graph. This axis here is a cartoon for the space of weights. We're just showing you one line here, but it could be multi-dimensional weights. And at this point, you compute the gradient. It's going to be a vector from this point. Its descent, it will be pointing down. And at this point, the starting point will give you a level of the cost function, which is often referred to the equipotential or cost curve. And correspondingly, if you map this one on the weight space, which is described here in cartoonly by a line, this vector here is going to show you a vector here. You control the length of this vector by this eta, and it's pointing this way. And if you have this weight, you want to move to a next weight by adding the contribution of the gradient. And because the system is gradient descent, you start here, you'll be pointing, going towards this minimum. And in this system, we have no problem. We have only one global minimum if the Hessian is positive definite. And you can look at the graph, but if you're sitting only in the weight space, you'll be just pointing towards this solution. So this alternate method says you don't have to compute the inverse because your MATLAB cannot deal with that. But here I give you this vector. And what are you going to do? You have this formula, which is you have the present weight vector. You want to compute the next weight vector. And you have the change in weight, which is represented by the gradient descent. And you plug in whatever the gradient descent is, which is this quantity in parentheses. And incrementally, at every step, you're going to improve and move towards that solution, global minimum, without doing an inverse. Okay? However, in this picture, we still haven't really said anything about how to get that expected value. We still have a problem with the expected value. You need to estimate it. If you know the density of your data, you're done. You just use that and estimate it. But in almost all practical problems, we don't a priori know the probability density, or the probability density could be a function of time, varying over time, okay? And so on and so forth. So with this one, you still need the expected value. Okay. So the least mean square is an approximation of this one, trying to basically bypass the offline computation of the expected value of the data. And it has some underlying assumption. When it first developed, people didn't really have the assumption. It was a practical technique that worked very well. But the interpretation of it is that you're going to have an online update, meaning that I'm going to update per sample or group of samples. The hidden stuff here is that I'm assuming that the data, the random variable data that I'm dealing with, is sometimes called ergodic, translated to the following, saying that the statistical ensemble of this data could be captured by a sequence or time averaging. Okay? That's what we mentioned last time. So we remove the expected value, and we see what we've got. And this quantity here, you can, from the same equations that we have before, remove the expected value. We can pull this x sub k out. This summation here is really the output, and we end up with this equation, which, by the way, we could have derived it from the cost function directly. So this equation, as if it has an expected value operator that's been removed, which means that I'm going to take a sample comes in, I'm just going to, per sample, I'm going to compute. Or perhaps maybe average it over a few samples to estimate the expected value. So a crude estimation of expected value. If the data is ergodic, that estimation is going to work. What you're doing over time is going to be over a long time. You'll be actually estimating the expected value. Okay? And this is the equation. So this whole thing of removing the expected value translated this technique that works in practice, and you don't need to walk around offline and compute the expected value. And you can just assume that over time, okay, you are estimating an average of this quantity, which is really the expected value of this quantity. What is this quantity? The gradient descent really translates to a product of the error signal at the output, and here the incoming sample. So the incoming sample and the corresponding error. Product and that will be corresponding to the gradient, and you decide the strength of that gradient by this eta, which is learning rate parameter. Often you want it to be very small to mimic the true gradient process, but you can control it to be as large as your process or computation or problem allows you to. And you have basically an algorithm that says, okay, I'm going to start initializing weights. Typically, in practice, what people do, they have random small weights. So here's the weights. I'm starting with 1. In Python, you only start with 0 in your counting. And you plug in those initial guesses of the weights. You have some sample, 1 or many, and you do this computation of the output. You compute the error. You plug in the error times the incoming input. That's how you update the weight. You could do it per sample, incoming sample, or you could do it over some samples, which is referred to as mini batch. So you can have mini batch, which is better than having an online. Online, basically, you take 1 sample at a time. Every sample, you update the weights. Okay? The mini batch is that you compute and you take average over a mini batch, which is a group. Often in practice, we select, 16, 32, in computational codes. Okay, 64, things of 128, numbers of that sort, which is a mini batch. And presumably the time average or the sequence average over that is an estimate of the expected value, the ensemble average. And that only happens if the data is ergodic, okay? And so that's the, I'm keeping a k, which is k in this case is the index from 1 to p, okay? And n is basically the step or the time, if you wish, or the index. And from here to here, I just said, okay, instead of writing this one as an element by element, I'm going to have this one as a vector. I'm writing here the weight as a row vector. I'm doing it for a row here by choice because I'm going to graduate to the matrix. So this is like the first row of a matrix corresponding to the first output. Okay? So here's the row. Here's the row of the weights at time n or stage n. And here is basically, when I have it as a row, this product of the error, which is a scalar. Now, the input is a vector. I have to take a transpose of that to have a row, row, row. It's always good to basically make sure that things are compatible. When you have terms on both sides of identity, you look at the matrix, the vector, and make sure the dimensionality is compatible. And often that guides you very well. It turns out, and you show the same process, if instead of a single input, I have a vector single output, I have a vector of outputs, I can, and therefore I have a matrix instead of a row. So in this case, the error is going to be a corresponding vector to the dimension of the output, and I can actually write this one here the same format. A matrix at time n plus 1 or stage n plus 1 equal to the present matrix, and that's how I update it. This product is a product which is called an outer product, okay, which is the vector of errors, which is the dimension of the output, let's say R, and here's the vector of the input transpose. So this one gives you the same dimension as the matrix. So this is going to be an R, for example, which is the number of outputs by, in this case, P. Okay? So my point here is that whatever you derive in this scalar, and then you look at when you have the whole row, the same form I'm keeping it when you have a matrix, which means you have many outputs, many inputs, and you have this particular relationship. Any questions on that? Yes?
Is it possible that the cost function is not a convex function?
Yeah, in this case, with a single layer, it so happens as a function of the weight, the function is convex. We'll show you immediately when we move to multi-layers, it's going to lose convexity. So in this case, we've shown that you have a single solution, because when you have a single layer, the cost function as a function of the parameters, which are the weights and the bias, will be convex function. The minute you have stack another layer, as we'll see in a second, it loses convexity as a function of the parameters. Even though you define a function which is convex, the L2 and L1 and norms and other things are all convex functions. But they convex function as a function of their input, which is the error. But they're not convex function of the parameter, which could be deeper in the network. So that's a very good point, and I'm glad you brought it in. That highlights the distinct things. When we move from this signal processing model into the multi-layer neural network, we lose convexity, and also we add nonlinearity, which adds more complexity. Okay? Very good. But the bottom line is that in this process, I'm showing you that you can move from the scalar to basically look at a row of parameters, which is the weight, and you look at the equation form, and then you have the same form showing up when the weight is matrix. In this case, we have a linear mapping, which is a linear filter, with P inputs. In this case, we're using P for the inputs, and we use, let's say, R for the outputs. And you have this format. Any questions on this formatting? So in general form, we will be adopting the case where we're going to split the bias separate from the parameters. So the bias here, which is a column vector, here's the output, which is a column vector, whatever dimensionality. And then you have a weight matrix, and you have a vector input, and we have the bias. And you think of the bias as having a signal which is equal to 1. And you can lump this bias with the input to have an augmented matrix. And you have, okay? But it turns out when we have multi-layers, it's good to have the bias separate for the convenience of computational things, for modularity, okay? And I'm showing you here, here's the filter, linear filter, which we view it now as a single layer. It's a linear layer. We haven't inserted any nonlinearities yet. And then the update law based on gradient descent is exactly like this form, where you have the expected value operator. To move into the so-called least mean square, you just take that linear operator, take it out, and assume you have ergodic properties, and over time, this computation, this outer product of a vector of error times the transpose of the vector of input, going to give you a dimension matrix of the same as the weights. So this is called an outer product. We have an inner product, which is two vectors. Apply inner product, you get a scalar. This outer product, which mimics the covariance matrix, is you have a vector times the transpose of the vector. The dot product is the transpose of the first vector times the vector. Okay? So this is outer product, which gives you a matrix. Two vectors, you multiply them, you get a matrix. Okay? And here, for the bias, it's similar. You have a vector bias, and what happens in this case is that the input for the bias equals 1, so you end up only with the bias expected value of the error. The bias only relies on the error signal to update. The parameters rely on the product of the error signal and the incoming input signal, because we envision the bias has an input equals 1, so it becomes the same scenario. So I have here basically people take this model and have taken this model over the years and analyze it from many directions and many means. And here's the same equations, and I rewrote it here in a different way, where actually this equation, I'm focusing on the parameter, the weights, and I expand this equation to have this one equals identity minus a covariance, or outer product of the incoming signal times the weight plus this outer product of the desired value, which is now a vector, that product. So this is the cross correlation, this is the autocorrelation matrix. Okay? And you could do analysis here because this represents, in terms of the weights, a linear system. Okay? However, this linear system has its own matrix, which is time varying. It's a function of the input signal. And it's driven by this one here. And this diagram is not really, this diagram you have to make sure that you have a transpose, which I'm not. So this diagram is not one-to-one with these things. Well, it's based on a different formulation when we take the transpose of these things. So here, this is driven by D and X transpose, not this one. So this is incorrect here. You have to have D and X transpose to have this one matching these equations. Of course, this diagram is for a case where you take the transpose of every side and you get this diagram. So the next thing, I'm going to update and remove that diagram, or update that diagram matches those equations. Okay? Any questions? How many people feel comfortable with this stuff? Because it is basic analysis, it's calculus, really undergraduate material, okay? But some of us maybe been away from this stuff for a while. You need to bring yourself up to date with this thing. How many people feel comfortable or have any questions on it? Any questions? Yes?
I have a question. I don't know if that
Sure.
makes sense at all.
Yep.
But when we remove, went from the expected value to using, I remember in Fathi,
Just remove the expected value.
learning.
Huh? Yeah, just remove the expected value and take the sample as they come in. Yeah.
So if I have 100 basically samples in my data.
100 samples, okay?
So instead of using the expected value or mean or anything, so I will go with one of them at a time.
You can apply one of them or a group of them, or a mini batch. Mini batch is more than one. So one or more. Decide what. So if you have 100, let's say you take 10 in
so
tens.
If I go with 10, then for each of those 10, I need to do the equation separately and then get the
You apply one at a time.
One at a time.
And then you average at the end. Yes, take the mean of them. Yeah. Any other questions? So so this is, whereby you're saying that I can't rely on this one sample, and the reason sometimes is legitimate because you could have an outlier. That one single sample is a noise. It's going to throw you off. You don't want the one sample to determine the direction of where you're moving. So you do it over many samples. You make sure you clean up the noise, and because every sample is going to correspond to a direction of the gradient. So by doing it over a group of samples, taking the mean, that gives you the safest direction without basically being overfit or being derailed by a single noise, an outlier. Okay? Very good.